We're in Chapter 9, and in Chapter 9 we'll be looking at diodes and diode circuits. Diodes are the first application we will look at addressing the use of semiconductors. And the first thing we want to do is to look at diode characteristics. A diode is simply a PN junction, but its applications are extensive in electronic circuits. Three important characteristics of a diode are: first of all, the forward voltage drop. Under a forward bias condition, this should be about 0.7 volts. Then there is the reverse voltage drop. When reverse bias the diode, the depletion layer widens, and usually the applied voltage is felt across the diode. Then there is the reverse breakdown voltage. Reverse voltage drop that will force current flow and in most cases destroy the diode. Okay, diode elements. A diode has two leads connected to the external circuit, and here we have a little diode here, and this would be the two leads. Since the diode behaves differently depending upon forward or reverse bias, it is critical to be able to distinguish the leads. Okay. The anode connects to the P-type material. Okay, this would be the anode right here. This is connects to the P material, and the cathode connects to the N-type material right here. And when you see a diode, there is usually a colored band on the diode, and the colored band indicates the end that is the cathode. And one way to remember the designation here is that the arrow always points to the N material. So the P material would be here, and the arrow was pointing at the N material, which would be the cathode. Ideal diodes. In an ideal diode, current flows freely through the device when forward biased, having no resistance. And this is ideally what should happen, or what we would want to happen, but this is not what will happen. In an ideal diode, there would be no voltage drop across it when forward biased. All of the source voltages would be dropped across circuit resistors. So there would be no drop across the diode. All of the source voltage would be applied across circuit resistors. In an ideal diode, when reverse biased, it would have infinite resistance, causing zero current flow. Now, practical diodes. This is what you'll actually see. A practical diode does offer some resistance to current flow when forward biased. Since there is some resistance, there will be some power dissipated when current flows through a forward biased diode. Therefore, there is a practical limit to the amount of current a diode can conduct without damage. A reverse bias diode has very high resistance. Excessive reverse bias can cause the diode to conduct. And practical diode forward bias. Okay, here we have a situation. The applied voltage is less than 0.7 volts. Now remember, to forward bias a diode, we had to place more than 0.7 volts across. With less than 0.7 volts, we won't be able to overcome the barrier potential, and so this will act like an open, and there will be no voltage drop in the circuit. Okay, here we have the same thing, only we have increased the voltage to 5 volts, and now there's enough to forward bias this diode. Notice 0.7 is dropped here, the remaining voltage is dropped here, the 4.3, so this is our 4.3 plus 7 equates to our 5 volts. If this was a 1K component here, then 4.3 divided by 1K, we'd have 4.3 milliamps of current through this resistor and through the diode. In this case, we have increased the voltage to 25 volts. Now notice that the voltage drop shown here is 0.8 volts. Ideally, we would say that it is 0.7. In this case, if this was 1K, then we would have 24.2 milliamps of current in this circuit, and there is some internal resistance in the diode, so as currents increase you will see the voltage drop increase a little bit, but usually we say that it is 0.7. Now, in some cases I have seen rectifier diodes where the voltage drop is as high as 1 volt, sometimes as high as maybe 1.2, but this is unusual. Usually we consider it to be 0.7 volts. Okay, reverse bias. Now here we have the diode in so that it is reverse bias. Notice the cathode is connected to the positive supply. Remember that N material here with all the electrons is going to be attracted this way, and so we're going to increase that depletion region in the capacitor in the diode, and so it looks like an open, so the 10 volts will be felt across the diode, and this is a reverse bias condition. In this situation we have simply increased the voltage. The same condition exists, except the depletion region is probably a little bit wider, and the applied voltage is felt across here, and there is no current in the circuit. Now here the applied voltage is greater than the breakdown voltage. We don't know what the breakdown voltage of this diode is, but it is greater than that, and so what's going to happen at this point is, even though it is reverse bias, current will be forced to flow through this device. The device is effectively breaking down, and we're going to have current. The current through here will be the applied voltage minus whatever drop there is across this device. This usually damages the diode. Okay, current versus voltage. In a practical diode, there is very little forward current until the barrier voltage is reached. When reverse bias, only a small amount of current flows as long as the reverse voltage is less than the breakdown voltage of the device. Now what we have a current versus voltage curve for a practical diode. And this is pretty generic in regard to diodes. You see all basic diodes look like this. Now there's some other diodes, special application diodes, that would be a little different than this, but this is the curve that you generally see in a diode, and the value that will vary would be this one here, the breakdown voltage. So what does this mean? Well, here we have the knee voltage, the barrier voltage, and the knee voltage, and remember here we're graphing voltage going this way. This would be voltage forward, and then this would be reverse voltage indicating reverse bias. So voltage in a forward bias condition, and this would typically be 0.7 volts. And then we're graphing current going this way. Now you see that this curve, it's not straight up, it has a gradual curve to it. So at 0.7 volts the diode begins to conduct, and then we begin to have what we'll call forward current. Now as the voltage goes up, I think we had we graphed 5 volts, and that would we'd probably have a current about here, and then we did 25 volts, and we said that we had about 0.8 volts, but you get the idea that if we graphed this and came down here, we'd see this would probably be about 0.8 in that particular case. At any rate, the forward voltage is typically 0.7, and then based on how much current is flowing through it, you might see a slightly elevated value above 0.7. Now, when we reverse bias the diode, you'll see that the current flow is virtually zero, and ideally it would be zero, but there is going to be a little bit of leakage, but for the most part we're looking at no current flow at all. And in reverse bias we would see this condition until we reach the breakdown point. Now at the breakdown point we're going to see a rush of current going in the other direction against the normal current path of the diode, and again this probably represents the destruction of the diode. Okay, this concludes our introduction to diode characteristics, and we looked at this last item we looked at was the current versus diode voltage curve for current and voltage. We also looked at the breakdown voltage, and we looked at a couple different reverse bias conditions as well as some forward bias conditions. We talked about the let's see, where was it? We talked about practical diodes, ideal diodes. Well, here it is. We look at the diode elements, and that concludes our look at diode characteristics.